So, hi everyone. So today we're very happy to have Shinsei Ryu from Princeton University giving us a talk about multipartitioning, topological phases, and quantum entanglement. Thanks so much. Please.
Thank you so much for the invitation. I'm very glad to speak here. So today I'm going to talk about entanglement in field theories and quantum many-body systems, and then that's something I've been working on. And then I looked at various kinds of many-body quantum systems, including holographic states. Today I'm going to talk about topological phases. So I'm not sure if this is something high energy theorists would be very much interested. But there's some technical part which appear during my talk that will perhaps touch upon some of the, at least the technical aspect of string theories. And then I'd like to learn more about this aspect, if there's any comment. So yeah, please interrupt me if you have any questions, and I'm happy to answer any questions. So this talk is based on this ongoing work, or in fact, it's a paper which will appear soon, and then that is done in collaboration with my graduate student Yuhan Liu, Jonah Kudra Fram, and also a postdoc in my group, Raman Soha. Okay. So I start with a brief introduction of topological phases, and then various quantum entanglement or quantum entanglement quantities, and then I will introduce the particular setup I am interested in. Okay. So just a brief overview of topologically ordered phases. So these are phases which are not described by a symmetry breaking, or not described by a, not detected by local correlation functions. These phases are very interesting because they support very exotic excitations, which we call anions. And then many quantum condensed matter physicists are interested in various aspects of these topologically ordered phases. Here's a quick summary by comparing topologically ordered phases with more conventional phases with spontaneous symmetry breaking, SSB. Basically, these conventional phases, they are well described by a paradigm of Landau-Ginzburg, or maybe Landau-Ginzburg and Wilson, where we can identify some local order parameter and we can basically build a description or theory out of it. For example, excitations can be described by a Navier-Wilson bosons built on the ground state and so on and so forth. In contrast, topologically ordered phases are characterized by the existence of these anionic excitations, and then properties of anions, which I'm going to review in the next slide. And then as a sort of a corollary, there's the ground state degeneracy, which are not associated to the symmetry breaking. We usually call them a topological ground state degeneracy. Basic framework to describe topologically ordered phases is a topological quantum field theory. Okay, so let me give a quick overview of the properties of anions. So anions are, as its name suggests, they're neither bosons or fermions. They have a quite exotic statistics. When we exchange two anions, they may have a phase which are different from -1. That is called fractional statistics. Or
sorry if I could ask a question now, because I understand, I don't know much, but topological field series can exist in any dimension, but anions only in 2. So do you have topological phase transition in other dimensions, or you are just looking at two? Or
that's right. Yeah. So thank you for asking. Here, I'm specifically speaking of 2+1 dimensions, and then yeah, I should have said maybe topologically ordered phases, they could exist in other dimensions, but topologically ordered phases in 2+ dimensions are characterized by the properties of anions. But topologically ordered phases can exist in a broader context. Thank you for asking.
Thank you.
And then the reason I'm interested in 2+1 dimensions is that they are kind of very physically relevant in condensed matter physics context. For example, fractional quantum Hall effect, which is characterized by the plateaus in this Hall resistance or Hall conductance, or there are other candidate systems realized in the lab. Anyway, coming back to anions, in 2+1 dimensions, topologically ordered phases are characterized by the properties of anions, and then they are well described by basically by using the word lines of anions. So these are typical descriptions of anion word lines. So as I sort of said, if I exchange two anions, we may get interesting outcomes such as the phase, which is neither bosonic or fermionic, or sometimes we could even get a state which is different from the initial state. So this is called braiding. This word line represents two anions of type A and B are braided. Or anions can split or fuse into each other. So two different anions, they can fuse into different kind of excitations, which here we call just C, and so on and so forth. And then this is basically diagrammatic framework corresponding to a given topological quantum field series. Okay. So now, so topological phases are, something we are very interested in, but they come with many challenges. And from the kind of experimental point of view, one challenge is how we detect topological data, such as the braiding or fusion of anions. How do you detect anions? And then problem for a very long time. There's the recent breakthrough at Purdue, which is a direct observation of abelian braiding statistics by this beautiful experiment, which perhaps I don't have to explain here. But it took a very long time to finally verify even the abelian braiding statistics. There's a other more exotic braiding statistics, which is non-abelian. Non-abelian here means if you braid two particles, you get the state which is different from the initial state. For more exotic braiding statistics, detecting them remains as a major challenge. From theoretical side, one could ask various other questions, such as which part of topological data measurable, or at least easy to measure or well defined, and are there relations between different measurable quantities? Are there any constraint, or are there any relations between different pieces of topological data? Or one could even ask, do we know all topological data to characterize topological phases of matter in general? There's a lot of questions. So I also want to mention one more experiment on a topological data, which comes with a topological order. So that's a central charge, or to be more precise, chiral central charge. So if you wish, this is the additional data to fusion and the braiding of anions. Physically, this can be measured by looking at the thermal transport at the edge of topologically ordered phases. So the thermal conductance is given by this formula, which is proportional to central charge. So this is another experimentally detectable or important data characterizing topologically ordered phases. And in recent years, in last few years, there have been finally the experimental measurement of the thermal Hall conductance in fractional quantum Hall states. I mean, in the quantum Hall setting, or in some sort of spin liquid systems. Okay. So this is the interesting development for these two experiments: braiding statistics and the measurement of chiral center charge. Today, I will focus more on the quantities which are related to quantum entanglement. Okay. So on the one hand, looking at entanglement may give us another probe to topologically ordered systems than transport type experiment. I mean, transport experiments are great in solid state systems, but for more artificial systems such as cold atomic systems or some other systems, it may not be easy. It may not be an easy experiment. And then on the other hand, entanglement in these synthetic systems, cold atomic systems, for example, it became possible to measure quantum entanglement directly. So it is interesting to look at entanglement quantities of various kinds to help us characterize topologically ordered phases. On the another side of theoretical physics, the quantum entanglement is also related to the, for example, the simulatability of quantum many-body systems. For example, state with a lot of entanglement, roughly speaking, is very difficult to perform numerical simulations in classical systems. Or if we know the entanglement structure better, we could perhaps come up with the efficient numerical algorithm to study topologically ordered phases and so on and so forth. So looking at entanglement may help us to develop such a algorithm, or at least intuitions into many-body quantum ground state. So in this talk, I will going to study a quantum entanglement. So I will first review the most famous entanglement quantity, topological entanglement entropy first. And then I will introduce the my setting, which goes slightly beyond the previous setting. And then I will just quote some result. Okay. So if there's no question at this stage, I will proceed to the first a topological entanglement entropy. So this is the one of the first entanglement quantity studied in topologically ordered phases. It goes back to this work, Levin and Wen and the Kitaev and the Preskill in 2005. So this is a very simple setting. So we consider ground state of topologically ordered phases in two space dimensions. Then we bipartition the total space into two regions, A and B. And then we look at the entanglement entropy for, let's say, for this region A. And then in two-dimensional gapped systems, the leading order term in the size of region A is given by this. So it's an area law term. But there's the what these papers found out was that there's the additional piece which comes with a negative sign, and then this log of D is the D is the quantum dimension, so-called quantum dimension of topological liquid, and that is a universal number that characterizes the topological liquid. So proposal was that to look at this constant piece, we may be able to detect a topologically ordered ground state. So this idea has been greatly explored. for example, in the numerical simulations for lattice quantum spin systems in two dimensions, people, for example, here, this is the particular Heisenberg model on the Kagome type lattice, and then they looked at the entanglement entropy as a function of the subsystem size, and we tried to see if we get the negative contribution as we interpolate this entanglement entropy scaling. Okay, so this is one example. And there's many other studies where we try to see this type of entanglement entropy scaling. Okay. So in this talk, I want to basically go beyond bipartition setting. By bipartition.
Can I ask you a quick question? So it's a very naive question. So if the system is gapless, there's still room for a constant term in the entanglement entropy. But
right.
Often, is there some sort of physical interpretation for that constant term as what's signifying?
Right, so that is the analogous to central charge. But in this dimension, there's no central charge, but that's something analogous to central charge. So the interpretation could be, I don't know, it's related to some extent the degrees of freedom we are having there.
Okay, thank you.
I think one difference maybe for conformal field theories, there may be more severe corner contributions. So if the boundary is not very smooth, there may be very severe corner contributions and so on and so forth. Yes, but you're right. So this type of scaling we can also study in gapless systems. Yeah, in particular in conformal field theories.
Thanks so much.
Are there other questions? So, right, so today I want to go beyond the bipartition. So here I'm partitioning the total space into two regions, A and B. But now I want to, let's say, multi-partition or tri-partition my total space. Here, for example, I can tri-partition the two-dimensional plane into three regions, A, B, and C. Or if it is a lattice system, it may be looking like this. But anyway, instead of bipartitioning, I tri-partition the total space. And then these entangling boundaries, they meet at the single point, like a junction, like a point. So that is the peculiar nature of this setup. So I will study this particular setup, and then I will compute entanglement quantities such as entanglement negativity and the reflected entropy, which I'm going to introduce in maybe the second slide. And then we try to learn the nature of topological liquid by looking at these quantities. So that is the goal of this talk. Okay. So let me first introduce a entanglement, one of the entanglement quantities we looked at. That is the entanglement negativity. So it is defined in this slide. So one motivation to study entanglement negativity is that it is the good quantum entanglement measure for mixed quantum state. So entanglement entropy is a good entanglement measure for pure state. In that it captures basically all quantum correlations. But however, if you have a state which is mixed, such as the finite temperature state, entanglement entropy captures not only quantum correlations, but classical correlation, like a classical entropy. So that's not the proper entanglement measure. But instead, we can take a look at the different quantities, such as entanglement negativity. So the definition is given here. So if I start from some arbitrary state rho in the tensor product Hilbert space HA tensor HB, Then we first consider a partial transpose of rho, which I'm going to define in a minute. And then once we get the partially transposed density matrix, then we just look at the spectrum of partially transposed density matrix, and then we consider this weighted sum of eigenvalues. We only sum over a negative eigenvalues that appears after partial transpose, and then we weight the sum by the mod of these eigenvalues. The partial transpose is a very simple idea. If I have an operator acting on the tensor product Hilbert space HA tensor HP, if I write the matrix element of partially transposed density matrix, here it's operator, partially transposed operator, I exchange only the indices related to the Hilbert space B. So here J and L. They are exchanged, but I don't touch the indices associated to Hilbert space HA. Okay, so that is the definition of partial transpose, and by using partial transpose, we define entanglement entropy this way. Okay, so the claim is that entanglement negativity, unlike entanglement entropy, it's a good quantum entanglement measure from the quantum information theory point of view. Okay. In particular, it extracts only the quantum correlations, and it doesn't worry about the classical correlations, which may be included in the mixed state density matrix. So in our applications, we consider first, we start from the ground state of the topological liquid, but we will trace out part of this Hilbert space. So I can, for example, trace out this region C. So then we get the mixed quantum states supported on region A and region B. So since it's a mixed state, it is meaningful to look at the entanglement entropy for rho AB, okay, by taking a partial transpose for either one of these two Hilbert spaces, A or B. So that's the first quantity, yeah, we look at. Yes.
Sorry. So when you said that it's a mostly measure of quantum correlations and not classical correlations. So this quantity, correct me if I'm wrong, but I was under the impression that it vanishes for some states that are not separable, but they have zero distillable entanglement.
That's true. That's right.
So do you have some sort of do you think that those states are somehow not appearing in is there some sort of, that sort of goes against the idea that
so that's right. So so there are some quantum correlations which a negativity cannot detect. Yeah, that's certainly true. And then it's also true that it slightly go against, that negativity can capture quantum correlations only. As far as I know, finding entanglement measure that can capture this, so to speak, bound entanglement is the sort of open problem in this field. So currently we don't have a very good quantity which we can apply to many body quantum physics, so to speak.
Thanks so much.
One thing which is true though is that negativity is a bona fide entanglement measure in a sense that it does monotonically decreases under LOCC. So that's an encouraging feature because that's almost like a defining feature of quantum entanglement.
Thank you.
So that is at least the one good feature for entanglement negativity. But yeah, I totally agree that entanglement negativity may not capture everything. Yeah, but that is something we can compute for many body quantum systems. Okay, maybe I should speed up a little bit. But are there other questions? Okay, so this is one of the quantities we studied. There's another quantity, or maybe perhaps I will come back to this. So another quantity we studied is the reflected entropy, and it is defined here. So we start from some some density matrix rho AB defined on the tensor product Hilbert space HA tensor HB. And then to define reflected entropy, we first consider a purification of rho. So what it means is that we consider a Hilbert space which is bigger than the original Hilbert space. Basically, we just double degrees of freedom. And then we write down the state in the doubled Hilbert space such that after tracing out this added degrees of freedom, we go back to this rho AB. So it's called a purification. And in this case, it's called canonical purification because the ancillary degrees of freedom we added is exactly the same as the initial degrees of freedom. This time, kind of a state we introduce, for example, in the context of sound field dynamics and sound field double state. Now, to define reflected entropy after purification, so what, as I said, if I trace out this introduced copy A star and B star, we go back to the original density matrix. But instead of tracing out A star and B star, we now trace out B and B star. Okay, so then we get the state supported on A and A star. Then we can consider the entanglement entropy or von Neumann entropy for the resulting density matrix. So that defines the reflected entropy, and this was introduced by in this paper that Faulkner in the context of holographic duality. In the holographic duality, this has a holographic dual description in terms of entanglement wedge cross section. Okay. I do not talk much about holography today, but we are going to use this reflected entropy to detect some properties of topological states. Okay.
Sorry, can I ask you a quick question again? Is it? I remember that in the original paper of Faulkner and Data, they said that it's not known whether reflected entropy is a LOCC monotone. Sorry,
yeah, so as far as I know, it's not the LOCC monotone. I thought it's not the LOCC monotone.
Oh, there are counterexamples, so it's not.
Yeah, I thought there's a counterexample.
I see.
Yeah, but at least it is not known it is monotone under LOCC, and I think there's a counterexample, yes.
And is it monotonic under partial trace or something? Like, does it satisfy some sort of data processing?
That's a good question. That I don't know. Maybe, yeah. But it's yeah, that I don't know. Yeah.
Thank you.
The other questions? Right. Okay, so now I defined my setup and I defined the quantities of my interest. So I just first want to quickly overview the result we got. So once again, we consider this type of setting where we multipartite the topological ground state, and then we computed the entanglement quantities, negativity, and then reflected entropy, and we also look at the spectrum. Okay, and then we look at the particular. We have a formulation which is sort of generic, but as a specific examples, we looked at chiral P-wave superconductor and the Chand insulator, which are like a very simple topological liquid. So we look at these examples. As a technical tool to study these quantities, we use bulk boundary correspondence, which we are going to review soon. So here's some of the results, which we will discuss more later. So we got the scaling of entanglement negativity as a function of the circumference or the length of the boundaries. And then it has this scaling law, which we are going to discuss more. And then we also computed the spectrum of partially transposed density matrix, which is usually called the negativity spectrum. And then it can be also studied for this combination of partially transposed density matrix. So we look at the eigenvalues of these objects. Yeah, maybe I just skip this for now, but there are interesting contributions to entanglement negativity the spectrum when there are anions in this setup. For reflected entropy, there's a recent proposal by this group at Berkeley. So they consider this combination, reflected entropy for AB minus a mutual information for AB. We consider this sum or difference. Sorry, it's not sum, difference. Then they claim that for topological liquid, this quantity is given universally by this after some optimization. So we are going to test their conjecture by using our method. At the moment, we are computing. We are doing computation. We actually did not know this conjecture, but we recently became aware of this conjecture, and we are able to test their conjecture. Okay. We also did some lattice numerical.
So what is C?
Yeah. So what? C. Yes. Right. So C. So topological liquid. If I make a boundary to the system, they support some edge state. And then edge state, they have their own central charge. So that's what is appearing here. What is important here is that this C is not the, as far as I understand, this C is not the chiral central charge, but the total central charge of the edge theory. Anyway, this is the central charge of the edge theory.
Thank you.
Are there questions?
Sorry, what is the recent claim? The recent claim is that the Markov gap is universal in what kind of setup when the regions touch?
Yeah, so their setup is exactly this setup we are discussing. And then they trace out, we trace out C and we look at the density matrix on AB. And then the areal terms in these quantities, okay, so I mean, okay, there's a, if you look at this difference, yeah, it is given universally by this.
But if the regions were not touching or you deform this geometry a little bit, would there be an inequality? Is this some sort of saturation of an inequality?
Yeah, so this good. So okay, so maybe I should say more. First of all, this is like a, yeah, okay, so this is how they want to present. So I follow their result, but I think I would say this is actually, it is more precise to put the inequality here. So this is the as low as we could get.
I see.
Yeah. Thanks. So starting from the given topological ground state, you may get something bigger than this. Then if you get such a ground state, you may be able to apply some local unitaries to remove some correlations, in particular short-range correlations. But once you remove these short-range correlations, there's some long-range correlations we cannot really remove just by local unitaries. And that is given by this.
Thank you.
So that is their claim. And then we are going to test this conjecture. Okay. Are there other questions? I guess this is just the highlight of the result. So we are going back to some more details for this result. Okay, so now let me quickly mention the kind of techniques we use. So we basically make use of bulk boundary correspondence, which is the one of the important properties of topologically ordered phases. So topologically ordered phases in 2+1 dimensions, we can make a boundary to the system, and then on the boundary there's the gapless degrees of freedom, and then that is described by 1+1D CFT. So there's a kind of rough correspondence between bulk wave functions. So bulk states, we have a ground state degeneracy. So we could have a multiplet of ground state. But there's a correspondence between the partition function we can discuss for the edge series. So there's a rough correspondence between, or maybe the correspondence between the bulk states and the boundary partition functions. We can also excite anions in the bulk, and that appears as the twisted boundary condition on the edge. That's once again how we make a correspondence between what's happening in the bulk and what happens at the edge. So we are going to use this bulk boundary correspondence. And more precisely, we basically follow this approach by Chi, Katsura, and Ludwig back in 2012. So they did this bulk boundary approach to compute a topological entanglement entropy. Okay, so we are interested in this setup. Here I'm taking a cylinder setup. So then I divide this spatial cylinder into two regions, A and B. And then I will trace out one of these regions. Let's say I will trace out region B to get the reduced density matrix on A. So I'm going to get rho A. And then I want to construct rho A by using this boundary conformal field theory degrees of freedom. So what this Chi, Katsura, Ludwig did is to consider a conformal boundary state within edge theory. So it's defined by this relation. And then what they found out was that at least near the entangling boundary, 2 + 1 dimensional ground state is approximated basically by this boundary state, which describes the excitation near these boundaries, if we smear it in some way. Okay, this is the approximate expression for the ground state, varied near the entangling boundary. But once we know the expression for the ground state, we can trace out a region A or a region B. For example, if we can trace out region B, that delivers this reduced density matrix on A. So in doing this, I integrate over one copy of edge theory attached to this region B. Okay, so then only the degrees of freedom in this region, in this edge theory remains. And using that degrees of freedom, this rho A is written in terms of these degrees of freedom. Okay, so I hope this is clear. So the physical picture could be summarized as a cut and glue construction. So I start from the ground state, which is fully gapped everywhere. It's a topological state, so it's fully gapped everywhere. But now I want to make an entanglement cut near here. So to construct the ground state near here, I first physically cut. But once I physically cut this cylinder, we see a gapless excitations for this region, for the boundary of region A and for the boundary of region B. Once we get gapless degrees of freedom, we can add some relevant perturbation connecting this and this edge state, which have opposite chiralities. Then we can try to gap the edge degrees of freedom by adding some relevant perturbation. The claim is that after adding such relevant perturbation, the ground state is given by the boundary state. So boundary state is not the ground state of conformal field theory, but once we add relevant deformation to conformal field theory, regular SL to vacuum is not the ground state anymore, but instead we get a boundary state as a ground state. So that is the basic idea. And we are going to extend this idea to the case of tripartition we are interested. Okay. And then I want to quickly review how it works for topological entanglement entropy. So using this idea, reduced density matrix, and in particular, the Renyi entropy of rho A can be rewritten in terms of boundary partition function. And once we get the boundary partition function, we can work with this boundary partition function. And then taking some limit, we basically reproduce the known result for topological entanglement entropy. There's this reading area law term minus this minus log of quantum dimensions. And here I put additional anions, so that's why there's another piece. But that basically, this is a way to compute topological entanglement entropy from edge theory. Okay, so we are going to we have to extend this idea or this technique to tripartition. So this is what we want to do. Let's consider a topological liquid on the sphere, on the spatial sphere, and I tripartition the spatial sphere into 3 regions, A, B, C, like this. It is convenient to deform this picture a little bit such that I kind of elongate this region by putting this region to this, and then putting this part of C to deform such that we make a cylinder out of it. And then I can think of this picture as a 3 cylinder, and they are glued together near here, which are indicated by this dotted line. Okay, so this picture looks now very similar, at least closer to this, except now instead of having 2 cylinders, 2 semi-infinite cylinders, we have now a 3 semi-infinite cylinders. And then they have to be properly glued to reproduce the ground state near these entangling boundaries. Okay, so we are trying to generalize this Chi, Katsura, Ludwig approach to this setup. So then I brought the edge state edge state coordinate here. So I have a 1 edge state here, which is the boundary of region C. And I have another CFT here, which is located on the boundary of region A, and similarly for the boundary of region B. And then I turn on some relevant deformation, which try to gap out this CFT degrees of freedom to recover topological ground state. Okay, so then I have to impose this condition, which is very similar to this boundary state condition we impose here. But since now I have 3 regions, 3 regions are kind of glued together by imposing this condition. Okay, so that's represent these interactions between these 3 edge series, represented by these dotted lines. So at first sight, we didn't know how to solve this constraint, but we quickly discovered that this is nothing but what people do in string field theory. So this is basically how string field theory vertex looks like. So there's the particular state in the conformal field theory, which describes the interaction vertex in string field theory. So we just call this vertex state. So vertex state is exactly what we are looking for, which satisfy this condition. And then consulting a string field theory literature, they also provide a way to construct this vertex state. The formal way to define vertex state is to consider state in the 3 copies of CFT or 3 copies of edge series. And then we impose this condition where inner product with its vertex state with some other state, sorry, this is 3, not n, reproduces the correlation function written here. And then this W1, W2, W3 are conformal maps, which basically bring 3 copies of disks. And then they bring, these conformal maps brings 3 copies of disk to a complex plane. For example, W1 take this disk and it map to a region in this complex plane, and W2 map the disk into this region, and then W3 map a disk to this region. So all three disks, which are separate initially, but after conformal map, they all meet on the complex plane. So this is the prescription or definition in the string field theory literature. And then we basically found out that this B does exactly what we want to have. Okay. Yeah, so I'm not sure if I'm doing a very good job explaining this, but if you have some questions, I can answer later. So this Vertex state we can construct by using the string field theory literature. We did it for particular examples of our interest, chiral P-wave superconductor, which has a chiral central charge 1/2, and Chan insulator with central charge 1. And once we get the Vertex state, we basically repeat this very similar calculation we did for the topological entanglement entropy, and we can compute the entanglement quantities of my interest. Okay, so that's a quick overview of the technical aspect. If there's a question on the techniques, I can answer.
Can I ask you a physical question about this particular tripartite state you're talking about? So this calculation gives you a tripartite state that supposedly has tripartite entanglement as well as bipartite, right? And are there like moduli, are there parameters that you could change in this calculation you're doing that would change the amount of bipartite versus tripartite?
Yeah, that's an interesting question.
That's what happens in holography, actually, usually.
Yeah, I think we may be able to change some modular parameter. So we are perhaps focusing on most symmetric situation.
Yeah.
Right now, I don't know how to change things, but it's perhaps possible, yes.
Okay, thanks.
That's perhaps possible if I start from these symmetric configurations and perhaps I act with some unitaries implementing some diffeomorphism or something like that. But yeah, that's actually a very good question. I haven't thought about it. Yeah. Okay, so this is a particular choice, and then but I focus on this choice, and then we computed the various entanglement quantities. So first thing we did was to compute entanglement negativity. This has to be done half numerically.
Sorry, yeah, and sometimes I think in string field theory you might need to insert an operator at the joining point to preserve supersymmetry, for example, or things like that. So
yeah, yes. So short answer is I don't know enough about string field theory, but yeah, there may be such things, and I don't know how it affects for our purposes, but yeah. Short answer is I don't know very much. Yeah.
Oh, thank you.
Yeah, so I would perhaps learn these things because that may be useful for my calculations, but right now we don't know. Right, so then the point is this Vertex state for the examples we looked at, they are just a Gaussian state, so we can compute correlation functions to compute entanglement quantities, and then this has to be done half numerically, but we did it numerically. So here's the quick result. First result I want to show you, and then one short comment is that boundary condition for these cylinders, ABC, they can be all different. Easiest choice would be to take a boundary condition. Here I'm talking about the fermionic, free fermionic edge state. So the boundary condition for these three cylinders, they can be all periodic, oh sorry, this is typo, or all anti-periodic or NS. In this case, there's no topological flux. Or I can take periodic boundary condition or Ramon sector boundary condition for these cylinders. So here I took the NS boundary conditions for all cylinders, or R boundary conditions for all three cylinders. So we did two cases. So here the result is tabulated here. The entanglement negativity, we found out that it scales in this form. So there's a leading area law term, there's a constant term, and there's sub-leading terms. And then this B-1, B0, B1, these coefficients are tabulated here. So the first coefficient, B-1, area law coefficient, is consistent with this expected number, pi c over 32. And then the focus is this constant term, which is supposed to be universal. If I take the NS boundary conditions for all these three cylinders, it is going to be very small. We actually think it is perhaps consistent with just a zero constant term. But once we put the Ramon boundary condition for all these three cylinders, that means I have a topological flux or world line of anions coming in for cylinder A, B, C. And then by the conservation of topological flux, it has to populate at least one anion at the junction. So that contributes to this universal part of the entanglement entropy, which appears to be near 0.33 in this calculation. Okay, so that is the first result I want to mention. We also looked at the negativity spectrum. So I think for the thinking of time, I focus on the spectrum of partially transposed density matrix. And then this is plotted here. So for fermionic systems, eigenvalues of this partially transposed density matrix, they turned out to be a complex. And then this calculation shows that it is eigenvalues are distributed over complex plane. And then it has some unique structure which comes with various branches. So first of all, there's a branch which form this circular shape. But there are also some eigenvalues which are very close to the real axis. So there are 2 or maybe 3 branches in this entanglement negativity spectrum. We don't quite know how to characterize this distribution. The only thing we can say at this stage is that it's a non-trivial distribution. Because for trivial phases, usually entanglement, the eigenvalues are concentrated on near 0 and 1, which I'm going to show you in maybe in 2-3 slides next. For other phases, we studied this negativity spectrum because we studied this negativity spectrum for other many-body systems. For example, for 1+1D fermionic CFTs, this negativity spectrum, we show that it has this 6-fold symmetric pattern. So this is the result of the calculation. So we are kind of hoping to characterize the distribution more to get the to relate it to the topological characterization of many body. The topological characterization of the topological ground state. Okay, so that's the another result, and I'm going to compare this with numerics later.
Can I ask you a quick question?
Mm-hmm.
So are there any known information theoretic interpretations for the eigenvalues of the transposed density? So the negativity spectrum you're talking about, for instance, is there some sort of a one-shot version that will capture the largest? Yeah, is there some sort of an interpretation for these? Are there Rennies you could construct that could have nice interpretation?
Maybe, yeah, we can certainly construct Rennies. So rather than just looking at the distribution of eigenvalues, we can discuss Rennies, which may be characterized by some.
But the eigenvalues are not real, right? So yeah. So you'll probably have to take the norm of the, yeah, it's tricky.
That's right. So if we take a norm, this is what you get. So this also has a very nice scaling, and once I take the basically a norm of, if I take a low dagger of this and then take a square root of this, and then eigenvalues are now all real, and then it is distributed this way, and then it has a perfect equal spacing structure, which maybe indicate the nice symmetries such as the conformal symmetries, but we right now we don't know how to characterize them.
Thank you.
Right. Okay, so I should perhaps finish in maybe 5 minutes. So the third result is about this reflected entropy. So we can compute this difference or Markov gap using our technique. And then this is the like a plot we get from our calculations as a function of epsilon. So this difference Markov gap is insensitive to ultraviolet cutoff. So then this value is also consistent with what they conjectured, the Berkeley group conjectured, C over 3 log 2. So yeah, our calculations is in favor of their conjecture. But this is only when I don't put any topological flux. If I put the Raman boundary conditions, then this HAB starts to depend on this regularization, UV regularization. Okay, but as far as there's no anions, we are in favor of our calculation is in agreement with their conjecture. Okay, so maybe I'll perhaps skip this, but let me just quickly say we also did the lattice fermion calculation. So we just take a free fermion calculation, which realizes the Chan insulator over quantum Hall effect, and then we can tripartite square lattice to get to compute various entanglement quantities numerically. Let me perhaps focus on negativity spectrum. So deep inside the topological phase, in the center of this phase, we computed the negativity spectrum, which shows once again the non-trivial distribution. So it has some circular shape, which is very similar to the continuum calculation we did. We didn't quite see the center branch, unfortunately, but it appears sometimes. So we are not entirely sure, but it is true that negativity spectrum has a non-trivial distribution deep inside the topological phase. Whereas if we are in the trivial phase, for example, here, distribution is centered around 0 and 1. So it doesn't have a, spectrum is not distributed all over the complex plane. Finally, I want to show you the numerics on reflected entropy. So we computed the reflected entropy for the lattice fermion system. And then if I compute this HAB as a function of the parameter of the lattice model, it has this curve. So we are going from here to here. And then near here, HAB is the smallest. And then there, the HAB is very close to basically 2 times this expected to this result. Which we think it's because our geometry has 4 trijunctions rather than 2 junctions. So maybe that's resulting in the factor of 2. But even with this factor of 2, it's slightly off, like 0.3 or 0.15. It's still off. That may be related to the short range correlations. Okay. So lattice model calculation doesn't really confirm the expectation. There's some non-universal feature maybe contaminating this result. Okay, so I think I have to finish. So this is summary. So we computed various entanglement quantities for the tripartition setup. And then expectation is that we get some topological data which are not captured by other quantities. And then we tested the conjecture by the Berkeley group, Mike Zaletel's group, which says reflected entropy minus mutual information captures total central charge. So our calculation agrees with their conjecture. And then this may have an implication for simulatability of such a state with non-zero central charge. And then, yeah, I just vaguely wonder if there's some interesting meaning or interpretation in the string field theory. And then there's other questions related to experiments and so on. Yes, thank you very much for your attention.
Thank you so much, Shinsei, for the beautiful talk. Are there any questions? I do have a question. So you calculate this for the geometric setup where you had this triangle, right? What if you did you guys also consider the case where B was separating A from C? So A and C are non-touching disjoint?
Yeah, so well, short answer is we have not, but we could consider like we can partition more, and then we can isolate B from A and C, and the B can, for example, touch with A and C only at one point, or we can also consider this type of torus system with this partitioning. Yeah.
Just naively, in the simplest calculation, I would have thought it would be interesting to look at like an infinite cylinder, cut it in two pieces. So there's A, there's a little bit of a finite cylinder, and then which is B, and then there's C. And I would be curious actually to know whether something like reflected entropy or negativity will scale with the size of L, the distance between the two half cylinders.
Yeah, so this is certainly possible. And then I did not look at this case, but somebody else might have, in fact.
Okay, all right.
I don't know the result.
Okay, thank you. Are there any other questions?
No, I don't know if at the beginning you said you had something on in the ADS-CFT or something that maybe you didn't have time to say, or?
Yeah, so right. So not in this work, but we looked at entanglement negativity in the context of ADS-CFT. We had the conjecture for the holographic dual of entanglement negativity in terms of the entanglement wedge cross-section. We basically, yeah, so that's one thing. And then we also looked at the entanglement negativity in random tensor network, which is related to holography. There's another, that's another work we did. And then we also look at the negativity spectrum for random tensor network. And then, yeah, so that's another thing we did. Yeah.
Thank you.
Are there any questions for Shinsei? If not, let's thank Shinsei again for the wonderful talk.
Thank you very much.
And thank you. So